Okay, thank you for the opportunity, and thanks to everyone for attending. Okay, so I'm going to be talking about the TES Beamline at NSLS-II. It's optimized for tender energies, spatially resolved X-ray absorption spectroscopy, and X-ray fluorescence imaging. First, I will introduce the Beamline and its capabilities, and then its design and some examples. So the Beamline mission is for spatially resolved microbeam scale spectroscopy and imaging of heterogeneous or structured materials, either natural or engineered materials, and small particles in a tender energy range, also in a non-vacuum environment. So it's friendly to samples that cannot be put in a vacuum. This includes static and in-situ operando measurements and covers a broad range of applications across a wide range of science. The design goals for the Beamline, kind of the Beamline vision that we had for it, were twofold. One is to optimize for the tender energy range from the source to the sample. So the entire Beamline is optimized for this. There are many hard or soft X-ray beamlines that can reach partly into the tender energy range, but with less than optimal performance. TES is optimized specifically for that energy range. The second goal of the Beamline is to bring the essential capabilities for X-ray absorption spectroscopy, including XAS, down to the micron scale without compromising to achieve the microfocus. Most beamlines that are set up for microfocusing were designed with the focusing as the primary goal. And in that case, they often compromise the spectroscopy capabilities. So the goal of TES is a particle or structure that's the same size as the probe beam. That's our challenge. And we believe we've succeeded quite well at achieving that. The tender energy range, TES will operate in standard mode from 2.0 to 5.5 kilovolts, but we'll be able to go down to 1.2 kilovolts with configuration change, swapping in monochromatic crystals. This covers the K edges of elements that are not readily accessible with hard X-rays, and also accesses uniquely advantageous L and M edges of heavier elements. It also will do a lot of imaging of light elements, especially in matrix with high potassium or calcium or iron that would normally swamp a detector. And so you want to set the incident beam below those edges to see lighter elements. The overall capabilities of the Beamline are to perform energy scanning in step or on-the-fly fast mode for spectroscopy, have a good energy resolution as good as Silicon 111 can do. This good energy resolution is essential for phosphoresceins in particular, where some of the differences in peak position are less than a half or a third of an EV, so you want to be able to resolve those. It has no measurable drift in energy calibration, scan to scan or over time, which is important for standardization. The beam size on a sample is tunable by the users from 2 to 25 microns about, with no adjustment to optics, just dialing up the beam size. The stage can scan an area of up to 100 millimeters or about 100 millimeters, also with fast scanning. Detection is either in fluorescence or transmission mode, and we can also do speciation imaging. So that's the capabilities in a nutshell. The challenges below 5 kilovolts are that we had to minimize absorbers in the beam path. The Beamline is windowless vacuum up to the end station. The exit window is a thin 12 micron beryllium window, and the sample chamber is a helium atmosphere. The Beamline optics are optimized for this energy range as well. Mirror coatings are nickel to avoid interfering absorption edges. The mirrors have to be pitched at higher angles to achieve harmonic rejection. And the monochromator motion can be very large range. For phosphorus XAS, the Bragg angle changes by more than 30 degrees. In this energy range, sample mounting is important. The standard use of Kapton tape is not very useful because Kapton tape is opaque. You also have to consider things of characteristics of the sample, such as sampling depth, particle size, self-absorption, etc. And in situ measurements are very challenging. Sample environments that are in use at above 5 kilovolts just won't work at this energy range. So we need to go to smaller micro cells, microreactors, or small sample cells, thin windows, very small path lengths, that sort of thing. So it's challenging, but it's doable. Now, microbeam X-ray absorption spectroscopy is a world of its own as well. It's very different from bulk spectroscopy. Bulk samples and standards are very heterogeneous at the micron scale. The picture on the right is actually part of a pellet pressed calcium carbonate standard that would be typical for a bulk measurement, but you see that the distribution of calcium is very heterogeneous on the micron scale. And so where do you park the microbeam to get a representative analysis from that sample? Things like that are very important to consider, such as particle size. Self-absorption is always an issue, but even more so at lower energies. And it becomes an issue of what's the self-absorption of what size particle that you happen to be hitting at the time. So you have to consider on a particle by particle basis what's your size and self-absorption effects. Most particles are single crystals at this scale and will have orientation effects that be considered. And sample surface topography, the relative orientation of the surface relative to the beam and the detector, must also be considered on this scale. So it's a different world, and you have to think about it that way. But it works very well once you have the right approach. The usefulness of microbeam spectroscopy is in part heterogeneous mixture in order to interpret or quantify the bulk veins. If you have a bulk spectrum that's a mixture of species, it helps to be able to go in and identify which particular species are present in the sample and where they are and what they're associated with. We can also combine the spectroscopy and the imaging and use the absorption spectra to select incident beam energies to perform speciation selective mapping. That's going to be very useful. Okay, so that's a quick introduction, and I've designed a break here as instructed.
All right. Do we have any questions yet? I have a question, but I'll wait until you get into the design. I think it's more appropriate then. I'm looking at chat. Here we go. Hang on. We've got some questions. First question is the pellet image from the last slide published anywhere?
No, I'm afraid it's not.
Okay. Kagesh, is your microphone working?
Yes.
Please ask your question. Please do.
Yeah, I have two questions. So first is, as the wavelength changes, the focal length will also change. So how is taken care while recording XAS?
Oh, the microfocusing is done by KBs, which are achromatic. So the focal length does not change with energy.
Okay. And while for what kind of in situ electrochemistry can be performed? Like what kind of cell will be suitable to do electrochemistry in situ?
Okay, we're testing a variety of microreactors and small cells. The space constraints are that you have about 100 millimeters in every direction to contain your entire sample cell arrangement. The windows have to be very thin, and the sample has to be very close to the window to minimize path length. It also gets inserted into a helium atmosphere. So although we have connections for gas and fluid feed-throughs and electrical connections, the cell itself, if you go up to a high temperature, you have to worry about heat dissipation. So keeping things very small, and if your reactor is getting hot, insulating it is important.
Okay, there's a few other questions, but they're, oh, sorry, go ahead, Kagesh.
Thank you. That was it.
Okay, thanks, Kagesh. There's a few more questions, but they're technical ones that I suspect might be covered in the next section of the talk. So why don't we continue? And thank you.
Okay, sounds good. Okay, so to jump right into the technical details, the overview of the beamline layout with beam from left to right. The source of the beamline is a bend magnet. Now, an NSLS-II bend magnet source is ideal for tests. When they first started proposing the design for NSLS-II and describing what the bend magnets, it has a critical energy of 2.39 kilovolts, so we limit the wasted power and extra heat load on the optics. The total heat load on the beamline is less than 100 watts, so, and it's spread out at the points where it's impacting the beamline. It has a very small source, ideal for focusing applications, and it's a broadband spectrum for energy scanning. So it's kind of an ideal source for this. The front end, we placed 2 mirrors inside the accelerator tunnel because the shield wall is at 25 meters, so it's, or 23 meters, so it's a long distance. In order to scoop up more beam, we put 2 mirrors inside the accelerator tunnel. The first mirror is a vertically collimating mirror, and the second mirror redirects beam for a fixed offset. We have a pair of mirrors because we want to be able to change the pitch of those mirrors for harmonic rejection. The pitch is adjustable from 6 to 20 milliradians. So these energies, we go to pretty steep angles. The mirrors are indirectly water cooled for low vibration. And they pass a vertically collimated beam to the monochromator. In the first optic enclosure outside the shield wall, there is a double crystal monochromator. It's a fixed exit design, normally run with silicon 111 monochromator crystals. We can also swap in indium antimonide or beryl. We're in the process of commissioning those other crystals. Then there's a toroidal mirror for primary focus. It's a one-to-one focusing to the secondary source actor, that's about 53 meters from the source. The focus at that point is about 1/4 of a millimeter, maybe a little bit less. Then beam diverging from the SSA is refocused by a pair of KB mirrors. The end station layout is shown on the bottom right of this slide. The spot size at the sample is user tunable from 2 to 25 microns at the sample, just by adjusting the size of the SSA. This is done at the expense of flux. So you just dial up the size of the SSA, get a corresponding change in the size of the focused beam. The end station hutch box, it's literally a box, it's about 1 meter long, and it's set up in the standard 45-degree microprobe geometry. Here's a photograph of the hutch box. You can barely see it, but there's a thin mylar film covering the entire face of the box that contains the helium atmosphere that's sealed. Then there's an outer door that closes it for radiation shielding, and that is the hutch. Going from left to right, there's an ion chamber for I0, then the horizontal and vertically focusing KB mirrors. What's unique about this KB system is that it's backwards of the typical geometry for a microprobe. Most microprobes have the vertically focusing mirror first, and then the horizontally focusing mirror closer to the sample. That allows better access for the microscope and to the sample. But in that case, the horizontally focusing mirror is facing the detector. So for this energy range, we wanted to minimize the scatter, so we swapped the positions of the vertical and horizontal focusing mirrors. So the horizontally focusing mirror is facing away from the detector. That may give us challenges for positioning the microscope camera, but we managed to do it. There's a periscope arrangement for the visible light microscope and camera aimed at the sample. The sample's at 45 degrees, and the samples are hung between those 3 copper bars in this particular sample holder, or we can accommodate larger samples. Behind the sample, there's a Canberra germanium detector, which works very well in this energy range, and it also does not have the silicon escape peaks, which would be murder in this energy range. We do have a vortex silicon detector just below that at a slight angle. That's also in use. And at the end, there's an ion chamber for transmission measurements. So that's a lot of things in that small box. One of the key things for the beamline is the beam positional stability. As I said, our ultimate target is microbeam XAS on a particle or structure the same size as the probe beam. So the probe beam has to not move during energy scanning at all. And so in this geometry, the beam position on the sample is defined by the SSA and the KB mirrors. It's independent of the upstream optics, which are more than 25 meters away. So any instability of the source or the upstream optics will translate to intensity fluctuations through the SSA, but not positional stability at the sample. That's the key there. Now, the important thing in that case is to keep the beam on the SSA. So we have two independent feedback systems that continuously lock beam position on the SSA. They compensate for drifts and for any beam motion during energy scanning. So even while scanning the monochromator on the fly, the feedbacks keep up with keeping the beam on the SSA. We have independent vertical and horizontal feedbacks that steer from the monochromator and maintain the beam trajectory within about 100 nanoradians. With that long of a lever arm, you have to be very, very precise in your control of the beam position. The vertical beam position control also has the added benefit of locking in the angle from the monochromator second crystal to the SSA. That defines energy. So this arrangement maintains a constant energy calibration. So there's no change in energy calibration or a shift of energy calibration with drift or thermal changes or during repeated scanning or over time. That's very important for this energy range where you can't continuously measure a reference edge in transmission. Okay, so that's the technical description. I imagine there'll be more questions at this point. So,
yeah, thank you. That's quite a beamline you're building. Let me scroll through real fast. Matthew, do you have some questions?
Yes, I do. One is I was thinking, based on my experience on ALS-1032, which this beamline resembles, that it would be useful to have a TEY detector. Like I did a series of sulfur standards with Alain Monceau, and that was really the only way to get around the overabsorption, what you're calling self-absorption. And yeah, so that's a helium box. And another question has to do with the XAS mode, or as I think you were calling it, energy scanning mode. Because I find that that if I do point-by-point XAS, that something's moving around such that the data are always generally noisy. But doing it by XAS mode, that averages that stuff out. And the problem that we were having on 1032 is that it was hard to synchronize the crystal translation, as the crystal gap, with the energy scanning. And down there at the phosphorus edge, that the beam height is definitely not fixed unless you do that. So I was wondering how you do that.
All right, so two questions. First one, TEY mode.
Right, so we are working on that. That's definitely something that a number of users are interested in. And so what we're working on is actually building that into a sample holder so that it's close enough to the sample so that we mount a number of samples inside that detector itself and mount that to the sample stage. That's one thing we're working on, because we do recognize that.
All right, and then the XAS question or comment?
Okay. Also, I do want to point out that I want to give a special nod to 1032 and Matthew, because they're in part an inspiration for this beamline. So the resemblance is not unintentional. So the history is that for people who don't know, I worked with Matthew in the early days on X15B at NSLS. And so I learned a lot from Matthew. Okay, so the question about the beam height as a function of quick scanning. This monochromator, we're actually using the X15B monochromator with a few modifications. So that monochromator it only has one motor driving the drag angle and crystal translation. So it is synchronized.
Aha. So it's a linkage.
Yes.
Okay. Are there more questions at this point? I have one, which is I'm curious if you've thought about how to add photon out capabilities to be able to do RICS or XAS.
I missed that last part, what you said?
RICS or XAS, have you thought about photon out capability?
We have. It's a fairly tight geometry there.
Mm-hmm.
But I think that's definitely something to think about on a small scale.
Mm-hmm. Yeah, there is an example of a spectrometer my group's made, and we've used it at SSRL, that uses a 10-centimeter Rowland circle, and is very compact. Maybe you and I should talk about that later.
Yeah, we also tried it at 1032, as you
right.
may recall.
That's right. Sorry.
But it turned out that with bending magnet flux, there just wasn't much count rate there. So it was more of a demo than real useful.
Okay, yeah. All right, so yeah, we should definitely ask about flux also. Let's see if there's any other questions. Not questions. Okay. All right, thank you. Then you should continue, Paul.
Okay. So now I'll move on to some examples of what we've been seeing so far. And there have not yet been too many publications because Beamline is fairly fresh. So I'll just jump into some representative examples here. A lot of the work done at the Beamline is on soils, especially phosphorus in soils, because phosphorus is an important nutrient for agricultural and bioproductivity processes. So it's the bioavailability of phosphorus is very dependent on its chemistry and its speciation. And soils are very heterogeneous. So this shows a fluorescence map of phosphorus, sulfur, and silicon of a soil from Japan. So you see the quartz grains, various clays, different shades of blue, and then a variety of phosphorus and sulfur distributions. So typically users are interested in finding the species in different locations. The large spectrum, can you see my marker here? I didn't try that before. Okay. So the blue spectrum is from this small phosphorus bearing grain, and that turns out to be an apatite calcium phosphate mineral grain. It has a characteristic shoulder above the absorption edge. The other spectrum from the more diffuse phosphorus spot to the left is phosphate adsorbed on ferrihydrite. And that has a distinctive pre-edge feature that's distinctive of phosphorus, of phosphate coordinated with iron 3+. So that's an indicator of that species. In the upper right are just a few microbeam phosphorus Zane's references just for illustration. So typically these fine scale measurements are used then to interpret bulk Zane's spectra and provide the spectra for multi-component fitting. So that's the typical use for soil samples. going completely the opposite direction from soils to space. This is an image from a slice of the Semchen meteorite, also in phosphorus, sulfur, and silicon. In this image, the blue grains are olivine crystals. The red is schreibersite and iron nickel phosphide. The green is troilite iron sulfide, and the black is iron nickel metal. We're below those edges, so they're just black. Makes a pretty interesting picture. If you look more closely at right about dead center of that image, there's a small green hairline through an olivine grain. So taking a very close look at that, we see that it's a very thin vein of sulfide in the olivine. And we did a close-up map with a very small beam, 1.5 by 2 micron beam at 2700 EV. And then we set the beam size to 4 by 8 microns, which is marked out in that small red rectangle pointed to by the arrow. That's the beam footprint for microbeam XAS. And we did the full XAS at the sulfur K edge and used that to identify what the structure was at that point. And we have not yet published that, but it's in prep, and it is not troilite like in the larger sulfide grains. As a second example from the same sample, but a different location, we also measured microbeam phosphorus XAS. And that was using a 5 by 10 micron beam. And again, the results are very good. You see very nice XAS signal using the microbeam. Looking at a different sample, but one in which we were interested in multiple elements. Looking at one very small particle in the center of it, it's essentially a 4 micron particle. We conducted the phosphorus, sulfur, and calcium zanes on that spot. The phosphorus and calcium zanes identify a calcium phosphate species, and the trace content of sulfur in that, much lower concentration, but that's present as mixed oxidation states. The peak at the left is a sulfide, and the tall peak in the center is a sulfate. These measurements were made with no adjustment to beam optics or sample position. We just dialed up those energies and made those measurements on that spot while sitting there. The next example is one of the examples of the in-situ measurements. This was a preliminary test of a small sample cell that was about, I guess the window was about 5 millimeters across, and the cell itself was about 5 centimeters in diameter with a heating element and containment and fluid connections. So it's a pretty small cell, and we did insulate it to keep it from losing heat to the helium atmosphere. The spectrum there is a phosphorus zanes. The catalyst in the cell was a phosphorus-doped silicate catalyst. There was a organic solvent there and reactants, and this was done at elevated temperature of 60 C. So it's not at extreme conditions, but it's real reaction conditions. And if you look closely at the spectrum, you see a shoulder in the left side of the peak up near the top. And pardon the quality of this because I just got it together quickly. But that shoulder is a feature that appeared only when the reaction ensued at the proper temperature. It was not there before the reaction was taking place. So we've succeeded in capturing a reaction with a catalyst. So that's a good example. There's really a lot more work to be done in situ measurements. So we're working with the Synchrotron Catalysis Consortium at NSLS-II to do more of that. For the topic of speciation imaging or species-specific imaging, using the incident beam energy that corresponds to specific spectral features characteristic of a given species or oxidation state works really well for sulfur, but we've also used it for phosphorus and uranium and a few other elements. This image on the right shows a fern leaf, the tip of a fern leaf. that's imaged for 3 different sulfur species in red, green, and blue. And the 3 species are distributed very differently across the leaf. This is very important, especially for biological samples where beam damage will change the speciation of any given spot. In this case, the red species, we were only able to capture by doing like 10-second zanes, 1 zap per spot, because after that it would start to change. So we had a very difficult time even capturing a glimpse of what that species is. But when we do the speciation imaging, the dwell time on any pixel for all 3 energies combined is only about 300 milliseconds. So we can capture the distribution of that species across the leaf with the speciation imaging. And that's really the only way to see it. If you were to sit on the spot and do slow zanes, you would miss this species entirely. However, doing this requires a very stable, repeatable energy calibration and good energy resolution. So we've got the beamline capability for that. Another example from space is a meteorite that has a lot of heterogeneity on multiple scales. And so we can make an image on the 5 to 7 millimeter scale, then zoom in with a decreasing beam size, just zoom in finer and finer to see more details. And then at any point, we can stop and look at a particular pixel, do phosphorus or sulfur zanes on that pixel. That's a typical type of measurement. Okay. Back to Earth on a geologic sample. This is an ore sample from Texas. And this shows a combination of using different K, L, and M edges. The sample matrix had a lot of calcium in it, so we want to go below the calcium K edge. But our target elements were sulfur and silicon at the K edge. We also looked at yttrium in the L edge fluorescence, and a trace of uranium looking at the M fluorescence. Did a very large coarse map and then a very fine detailed close-up map showing the relationship between a yttrium carbonate phase and some uranium-bearing carbonate phases. We also were able to use the uranium M5 edge to determine the oxidation state of the uranium. The M5 edge has a very sharp peak that has a distinctive position for uranium-4 versus uranium-6. So there are a lot of, it's not just limited to the lighter elements, but there are a lot of edges of heavier elements that are of interest in this energy range as well. Many of the catalysis users are looking at the platinum M edge or the zirconium L edge. Some of those edges are more sensitive to particular chemical interactions, so it's very useful. And the last example is an interplanetary dust particle. And this is a sample that's composed of many small grains. Most of them are submicron. And they're sort of spread out in this sample amount, so it's not ideal, but we are able to isolate submicron particles with a 2-micron beam and still get the phosphorus and sulfur zanes to identify different species. That leads into our future plan, which, in addition to additional more in situ measurements, we've got a large interest in pushing the spatial resolution even farther. So NASA has given us funding for a new second sample chamber to be installed downstream of the existing end station. And that will refocus the microbeam to a submicron resolution using a zone plate optic. This will do fluorescence imaging and spectroscopy. In this case, the spectroscopy will be somewhat limited because of the zone plate optic. But this end station will not interfere with the current capabilities, which will remain intact. In fact, to make measurements at the submicron end station, all you have to do is move the sample out of the beam path in the microbeam station, and then send beam down to the submicron station. This is part of a going program for extraterrestrial materials, which is overall geared towards samples returned by remote missions. For example, the current NASA mission OSIRIS-REx is collecting samples, or will collect samples later this year, from the Bennu asteroid, which is shown in the picture to the right. It's about 2 billion miles away, so it'll take a few years for it to get back, but it will bring back samples from that asteroid. And that's the type of thing that we're particularly interested in looking at phosphorus and other life-relevant nutrients in. So that's all I have, and thank you for your attention.
Thanks, Paul. That's wonderful. A suggestion, quickly jump to an earlier slide. The animation is taking up your bandwidth.
Oh, sorry.
That's okay. Liz Cottrell, you had a question. Is your mic on?
Yeah, sure. I just unmuted myself. Can you hear me?
Good to go.
Okay.
Yes.
Great talk, Paul. I'm just so interested in this. I am a user down at the XFM Beamline. So we've met. I don't know if you remember me, but
yeah, I've met you there. Yes.
So this is all really great. I wonder if you could say a little bit more about how you're preventing, I guess preventing is not the right word, how you're capturing spectra prior to beam damage. And is this, I guess I didn't understand technically what you were doing back there. It looked like you were capturing the spectra in a shorter amount of time. We have beam damage issues even in glass, and have been, doing things like defocusing the beam, trying to reduce the flux, the photon density on the material. And can you explain again the technique you're using here?
Okay, I'll go back to that slide. Okay, so in samples, typically at sulfur for a Zane's measurement, a spectrum takes about 30 seconds. And then we collect multiple spectra to average to get good statistics. So we monitor changes from scan to scan to look for beam damage. Mm-hmm. In instances where we see that there is beam damage, if we can make measurements by doing one scan, then moving, then doing another scan, then moving, so you don't sit on one point for more than one scan at a time, we can address it that way. But what I was talking about with the speciation imaging is that if we do that to at least obtain one spectrum of some species that we think damages very quickly, but then we can set the incident beam energy to a characteristic peak in that species and make an image of the whole sample. So we can image the distribution of a species without actually doing a full Zane scan at each pixel, which saves a lot of time and dose.
So that
sample damage radiation.
I'm just saying that allows you to make a species map.
Right.
Okay. And what kind of sulfur concentrations are we talking about here where you can collect the scan in 30 seconds?
Well, a 30-second scan is a little bit noisy, so we would normally do 10 or 20 of them.
10 or 20, 30-second
this is,
scans.
Yeah. This is a biological sample, so probably on the order of 1,000 ppm or 2,000 ppm in a light matrix. So it's not a very weak signal, but it's not high concentration either.
And in the meteorites, have you looked at beam damage for your sulfur species, or
I've looked for it, and I have not seen. Generally, I have not seen beam damage. I do keep an eye out for it in everything I look at. Most of the geological or meteorite samples, we don't see beam damage on the scale of the measurements that we make. This is TES does have a lower flux than XFM. I know XFM is a very hot beamline. So that it's already got an advantage there.
Okay, a couple more questions. There was a question about whether you've done or plan to enable doing studies in liquid jets.
I've seen a few proposals for that. I think it should work. We have not tried it yet. It's a bit of a challenge inside the helium chamber, but it seems very possible.
It's at 1 atmosphere, so yeah, there's a good chance it'll work out. Another question is, for example, this scan or the scan of the meteorite sections, how long does this kind of an XRF map take to do?
Okay. The larger maps that I showed were typically 4 to 8 hours.
Okay.
The smaller, finer maps were 1 to 2 hours. Even though they're a finer scale, they were a much smaller area.
Okay.
We've done a few overnight maps too.
Richard, you just put up a question. Can you turn on your mic?
Sure.
Please ask, yes.
I have a question. I have trouble saying what I mean, but there are detectors which have a hole in the middle, so you can put excitation radiation through the detector, and then your detector is flat to the sample, and therefore you have a highly increased solid angle of detection, like on radiance. Did you consider using such a detector?
We considered it, but typically those detectors are used in vacuum. The Maya detector is used in higher energies, but then that has a thick window. So the detectors themselves typically have to have cooling and a vacuum environment around the detector. It's inside the detector. So you either have to have a thicker window, or have the entire sample environment be vacuum. So that was kind of prevented it, because we couldn't do either one of those. So we decided to go with the standard 45-degree geometry. We can move the fluorescence detector very close to the sample to get a fairly large solid angle.
Okay. I have a somewhat related question as a follow-up here, which is there's been a couple of talks in this series about the transition edge sensor arrays. And you would have enough flux, certainly, to use those as your higher resolution detection. And I'm curious if that's something you've thought about.
It's something we're starting to think about, because that does seem like a very attractive option. The challenge again is the interface to the helium chamber, but that should be manageable.
Okay, seeing no other questions, thank you for the wonderful talk, and congratulations on completing the beamline and being well into commissioning and beyond. And the whole community is really excited about this, so congratulations again.